Good afternoon, everybody. Thank you for coming to this EMPA colloquium of today. Today is a pleasure for me to announce Professor Nicola Spaulding. Professor Spaulding got her PhD in chemistry at the University of California, Berkeley. And she's originally from England, from Cambridge University. As a research experience, she was a postdoc in Yale, and then assistant and associate professor in Santa Barbara Materials Department, and then full professor there. And since last January, she is full professor of materials theory at the Department of Materials at ETH Zurich. And she is working in modeling materials at different aspects. And her interest is mainly in design and investigation of novel materials. So among the topics that she has been facing in the last years, where I can cite magnetoelectricity, capacitors with interesting interfacial properties, antiferromagnetic domains, epitaxial strain, and also some more fundamental topics like origin of ferroelectricity, or the existence of the dipole moment of an electron. And today she's telling us probably something from both worlds, with the talk using density functional theory to design new materials, from magnetoelectronics to a theory of everything. Thank you very much for coming to EMPA.
Thank you, Daniela. And thank you very much for the invitation to be here. I've had a really fun day learning, I think, just a little bit of some of the exciting research that you have going on in various groups here at EMPA. So as Daniela said, in my group, our main expertise is electronic structure calculations using a technique called density functional theory. And I'll talk a little bit about what that is and what it enables. And I want to specifically tell you about how we use these tools to design new materials with specific targeted functions before they're synthesized, to predict them in advance of their synthesis. And I'll do this with illustrate this with two projects. One is in collaboration with the experimental group of Ramesh at Berkeley to make materials in which we can control the magnetic properties with electric fields. So these are called magnetoelectric materials. And the other project is kind of actually similar in material type, but kind of different in application, which is to test extensions to the standard model in collaboration with the experimental group of Steve Lamoureux at Yale University. My theoretical collaborators, whose work I'll be particularly featuring today, are Claude Ederer and Alison Hatt on the Magnetoelectronics project. Claude is now a junior professor at Trinity College Dublin, and Alison is at the Molecular Foundry in Berkeley. And for the theory of everything, Mariana Lajajic, who's now a junior professor in the research center in Jülich, is the main contributor. This is not ETH Zurich, as you can probably tell. This is on the beach outside the lab just before we moved to Zurich. Okay, so again, my goals are to really illustrate to you how electronic structure methods based on density functional theory can be useful in designing new materials. And my two examples are from a field of what are called magnetoelectric multiferroics. And so I hope to also give you a little bit of an overview of some of the excitement in this field and some of the applications. Device physics for electric field control of magnetism, and high energy physics to measure the electric dipole moment of the electron. If you get bored during the talk, you can kind of contemplate what that means for an electron to have an electric dipole moment. This is something I still have, as a materials scientist, have trouble getting my head around, but we'll talk about that a little bit. Okay, so how do we go about designing new materials? We're sitting not in the lab because we're theorists, we're sitting in the office or in Starbucks and we're thinking, well, I want to make a material with a specific property. Where do we start? And I want to show you the most fun piece of propaganda. Maybe no, the second most fun. I'll show you some more fun later. But this is a colleague of mine, Sam Bader from Argonne, was interviewed about the deficiency or the concern in the US about there being insufficient rare earth elements and those that are available, but mostly being in China, or the perception that those that are available are in China. And he said, well, I think he was trying to say all is not lost because theorists these days are able to design new materials with specific properties and try using materials without rare earths. And he described our design process. To create the material, the scientists described the properties they sought to a program that runs on a supercomputer, and it gave them the design for the material. And initially I was a little bit upset about this, but I thought about it. It's not so far from the truth. There's a little bit of human input in, we have to, of course, write the programs that run on the supercomputer, and we have to be a little bit more specific. We can't just tell it, we have to understand the properties also. But this is kind of somewhat in the direction of what we do. For a little more detail, or a little more kind of truth, we more or less follow this kind of scheme. So our first job is we have to decide what we want our material to do. So we need to identify the functions that we want to incorporate and decide what we think is the most important thing to spend our time doing. And then we have to understand really the chemistry and the physics that cause these functionalities. And this obviously, we use a lot of tools, experimental data, our calculations, and historical intuition, and so on. Once we understand what kinds of chemistries and physics cause a particular function, then we propose trial compounds. So we take a guess at the chemistries, the arrangement of atoms, the crystal structure, and that we think might do what we want. And obviously we don't do this kind of out of nowhere. We have, usually we're starting from modifying an existing compound by changing the structure or changing the chemistry or changing the symmetry a little bit. And then sometimes, or often first, we will go calculate the structure and compute the properties. Sometimes simultaneously with our experimental colleagues, we'll synthesize the compounds and measure the properties. And if we're lucky, what we compute is what we measure. Sometimes, or maybe often, this is not the case, and usually this is because our experimental colleagues have not put the atoms in the right place, or they've put in extra atoms that weren't supposed to be there or left some out, and they have to go and work on better synthetic methods. And many of the developments in the magnetoelectrics and multiferroics field that I'm going to show you have really been driven by improved methods for thin film and single crystal growth. Sometimes it's because the theoretical tools we had available weren't appropriate for the problem, and we have to go back and make improvements here. But when we're lucky, what we compute is what we measure, and when we're even luckier, what we measure is what we want, and we're done. We've really designed our new material from first principles. If what we compute is what we measure, but it's not what we wanted, then things get really interesting, because we have to go back to the start and say, well, why didn't we understand what would make a material ferroelectric or would make it magnetic? Because we've kind of, everything's been rational, but we haven't ended up with what we wanted. So I'm going to talk you through this kind of scheme for the two examples, two material types today, so you can see how it works. Okay, so the function in both cases, the principal functionality that I'm going to need in both the examples I'll show you is what's called magnetoelectric response. And so usually, if we want to control the electrical properties or tune the electrical properties of a material, we do that with an electric field. The electric field is the conjugate field to ferroelectric polarization. So we can switch, for example, the ferroelectric polarization, the spontaneous electric dipole of a material using an electric field. And likewise, if we want to, for example, reverse the ferromagnetic magnetization in a data bit in a hard disk drive, we do that with a magnetic field. And so this is the usual route to controlling properties, is to use the conjugate field that's appropriate for those properties. In a magnetoelectric material, we instead want to be able to modify magnetization with an electric field and electric polarization with a magnetic field. So rather than using this direct coupling, we're exploiting the cross-coupling between the field that's not the usual field for driving that property. And such magnetoelectric materials are a subset of a kind of larger umbrella class of materials that are perhaps a little more well known, which are called multiferroic materials. So the picture we just looked at is kind of this side of the triangle here. And a multiferroic is defined to be a material that exhibits two or more coexisting primary ferroic orderings. And so the example that's going to be relevant for us is that it's a ferroelectric material. It has a spontaneous electrical polarization that's switchable by an electric field. And simultaneously, it's a ferromagnetic material. It has a spontaneous magnetization that's switchable by a magnetic field. And when you have both of these properties coexisting, then by symmetry, it's always possible to have magnetoelectric coupling. One can then with an electric field modify the magnetization, and a magnetic field modify the polarization. One can also have ferroelasticity, a spontaneous deformation switchable by an applied stress that can coexist with ferroelectricity and ferromagnetism. But these days, when you hear the term multiferroic, just kind of by convention, it's usually referring to coexisting ferroelectricity and ferromagnetism. And that's what I will, the kind of multiferroics I'll focus on today. This has lately become quite fashionable. This is a plot of the publications per year over the last 25 years. If you do a search, I think this was for Magnetoelectric star, and you can see that there was not very much interest, or not very many publications at least, until rather recently, and then there was suddenly a rather sharp turnaround that was really enabled by two things. One, practical routes to multiferroic, well, I guess it's kind of one thing. Practical routes to making new multiferroics were identified because there's a community. We developed more understanding of how they should occur. And then once we were able to make multiferroics, then there was a lot of exciting work could be done. You can see there was also a little blip in activity back in the late 60s, early 70s. We're a little concerned. We're kind of waiting for this turnaround to happen up here, but at the moment it still keeps going up. The reason for the interest, for my interest, is really fundamental. It's very challenging to control an order parameter with the field that's not the conjugate field for that order parameter. So it's a challenging research problem. I'm also going to show you the most fundamental physics I've ever been involved in, which is the design of a material for a tabletop experiment to test extensions to the standard model. So there's some very fundamental physics that one can explore using multiferroics. From a technology point of view, even though the magnetoelectric response works both ways, you can do electric field control of magnetism and magnetic field control of electric polarization, it's really the electric field control of magnetism that's the technological driver, because a magnetic field requires a coil of current, which gets hot, and it's heavy, and it's bulky, and it uses a lot of power. So if one could do all of our current magnetism technologies but control them with electric fields, then this would immediately offer huge advantages in terms of power consumption, miniaturization, and so on. Okay, so I hope I've convinced you that I'm not completely mad to spend my time wanting to make magnetoelectric and multiferroic materials, and that I'm going to be and that there's a strong motivation for designing new materials with these functionalities. Okay, so now where do we start looking? What kinds of chemistries are going to be appropriate for making multiferroics? And my focus, and the focus I'd say of the field to date, has been largely in the class of transition metal oxides, and there are multiple motivations for this. This is a plot of the abundance of atoms in the Earth's crust, normalized to 10 to the 6 atoms of silicon is 1 here, as a function of atomic number. And you can see that there's no chance that we're going to be running out of oxygen anytime soon. In fact, if we run out of oxygen, we have more things to worry about than new multiferroics. The transition metals also are very abundant, and their compounds with oxygen are abundant. They tend to be non-toxic. They tend to be stable. They've already oxidized, so they don't oxidize further often. So from a practical point of view, they're very desirable. From a chemistry point of view, oxygen and its compounds with transition metals occupies really the perfect place in the periodic table, in that its bonds with transition metals are not too covalent and not too ionic. If you move to the left in the periodic table and look at the nitrides, they form very stable, strong covalent bonds, and materials then that have very good semiconducting properties, but from a functional response to external perturbations, they're not terribly interesting. On the other side of the periodic table, in the fluorides, you have very strong ionic bonds, which again are not very perturbable by external fields. The oxides are just in between, and they have as a result, have very strong polarizabilities, which are desirable for dielectric and ferroelectric properties. The transition metal part, particularly the 3D transition metals, we chose because they have what are called strong correlations. And what I mean by that is that the behavior of an electron somewhere in the solid really explicitly influences the behavior of all of the other electrons in the solid, not just in a mean field picture. If I flip a spin somewhere, all the other electrons really respond to that. And this strong correlation physics is associated with many exotic phenomena such as novel superconductivity, colossal magnetoresistance, unconventional magnetism, and so we thought likely multiferroism also. And again, from a practical point of view, the transition metal oxides exist with very many chemistries and in many structures, and also many dimensionalities. So we have a very rich toolbox, a kind of palette of crystal structure types to play with. Given that, even though there's this large diversity, both of the example projects I'm going to show you today, we use the perovskite structure, which, just for review for those of you who are not working all day on such structure, there's a transition metal ion that's octahedrally coordinated by oxygens and kind of a hole, a cube octahedral interstitial between the octahedra, which is filled by a second cation, usually a large cation such as a rare earth. So this is where we're going to start looking for our multiferroics. Anybody have any questions before we go on? Feel free to shout up if you have questions as I'm going. Yeah. Okay, so the first question that we set out to answer when we started working about 10 years ago on making new multiferroics was, why aren't there any? If you think of your favorite ferroelectric material, say barium titanate, lead titanate, they don't have any magnetic ions in them. And your favorite magnetic material, is probably, I don't know, probably iron as a guess, is not ferroelectric. And it was not clear to us at the time why this was the case. I think the answers were already perhaps known by or the answers existed, but they'd just not been connected between the magnetism community and the ferroelectrics community. And so let me give you just a quick summary of why this is. Basically, there's nothing fundamental prohibiting the coexistence of the two properties, but the kinds of chemistries that give you good ferroelectricity are different from the kinds of chemistries that give you good magnetism. So I think the magnetism part is a little easier to understand. We know that whether our electrons exist in a solid with their spins parallel, or whether they pair up and put their spins anti-parallel, depends on a competition between the Pauli principle, which would like the lowest energy orbitals to be occupied first with anti-parallel spins, and the Hund's exchange, which would like the electrons to sit parallel to each other. And so this competition between which term dominates makes, for example, sodium be non-magnetic and iron be magnetic. The band energy is bigger in sodium, the exchange energy, the Hund energy, is bigger in iron. And it turns out that the balance is tipped towards magnetism whenever you have partially filled d orbitals. You can kind of look at the balance between these two terms, and you can see that basically Hund wins over Pauli for partially filled d orbitals. So we need, if we want to have magnetism, to have atoms in there that have partially filled d orbitals. For ferroelectricity, it's a little harder, I think, to see this kind of intuitively, but there's a competition that decides whether my transition metal in green here sits at the middle of my oxygens or whether it off-centers from the middle. And here the competition is between covalent bond formation between the transition metal and the oxygen, which is favored over here when the transition metal moves close to the oxygen, and Coulomb repulsion between the electron clouds, which is favored if the transition metal sits right in the middle of the oxygens. It reduces the Coulomb repulsion between the electron clouds. And it turns out that the ferroelectric, the off-centered dipolar arrangement, is favored when the d orbitals are empty. Okay, so this kind of competition now between Coulomb repulsion and covalent bond formation, the covalent bond formation, which gives me ferroelectricity, is favored by empty d orbitals. And this was observed, actually, there's a beautiful paper from 1949 by Bernd Matthias of superconductivity fame, where he points out empirically that all ferroelectrics have empty d orbitals on this transition metal. So this was well known. So you see that immediately the problem. If I want to have magnetism, I need to have d electrons on my transition metal. If I want to have ferroelectricity, I need to not have d electrons on my transition metal. And this is the basic reason why if you just go randomly dig a perovskite out of the ground, it's going to be one or the other of magnetic and ferroelectric, or maybe neither, but it's not going to be both. So we understand now how to put it the community now understands how to put magnetism into a material and how to put ferroelectricity in there, and we have to think about how to put them both in together. And the field of multiferroics over the last 10 years has really been extremely active in thinking about new, clever ways of making things ferroelectric, of inducing a spontaneous dipole moment in a material. And there are now maybe 5 or 6 new routes to ferroelectricity that have been identified, which are really clever. And I'm not going to talk about those. I'm going to talk about perhaps the least clever one, which is the one that we've been pursuing. So one very obvious way that I can combine magnetism and ferroelectricity, if I know that I need to have a cation with d electrons for magnetism and a cation without d electrons for ferroelectricity, is to take a compound with 2 cations and make one of them have d electrons and one of them not. And so this is the approach that we've been doing. And remember, in the perovskite structure, there's a transition metal cation here, and there's a second cation here. So I have 2 choices. I can make this one be magnetic and this one ferroelectric, or I can do it the other way around. Let this one be ferroelectric and make this one magnetic. And I'm going to, actually, the examples I'm going to show you, the first one, we use this approach, and the second one, we use this approach. So you'll see that they both work, and there's very definite reasons to choose one or the other. Okay. Any questions before I launch into the first design project? No? I should tell you, all the PhD students, I won't stop until a student has asked a question. And I do not tire easily. So if you want to go home tonight, you should, find somebody, designate them to ask a question, and buy them a beer afterwards. Because I can go on and on and on. And you may want to go home at some point. So, okay. So let's go on to the first project, which was to design a multiferroic, a material with coexisting ferroelectricity and ferromagnetism. This is good. People are trying to think of a question down here. I can see. This is great. Coexisting ferromagnetism and ferroelectricity. And we'd like, if we want to do devices, we'd really like this to happen at room temperature. That would be really great. We'd like to have very strong polarization and strong ferromagnetism. And let me show you what we came up with. So our trial compound is perovskite structure bismuth ferrite. And this was a material, we can't really take too much credit here. It was known to exist already, and it was known to form in very bad perovskite structure crystals, or very dirty kind of black. Actually, I think I forgot to put in a picture of the early bismuth ferrite crystals. It was, there was some dispute about exactly what the magnetic ordering was. There was a number of different reports. It was reported to be ferroelectric, but with a very tiny polarization. So there was some data, I'd say, on very old samples that were very inconclusive. So the idea here is that, so the magnetism is obviously coming from the iron 3+, which has 5 d electrons. It's as magnetic as a transition metal can get. The idea for the ferroelectricity is that bismuth, trivalent bismuth, has what's called a stereochemically active lone pair. It has a pair of electrons that are not tied up in chemical bonding, and they localize just like the electrons in ammonia localize and make ammonia not trigonal planar. So remember from your introductory chemistry class, in NH3, the hydrogens are pushed down from the plane, and there's a pair of electrons that kind of are pushing them out the way. And ammonia has a dipole moment because of this. It's negative at the top and positive at the bottom. And so it's kind of a little ferroelectric. And it's ferroelectric because of this stereochemically active lone pair. Trivalent bismuth is really stereochemically active. It has a really strong lone pair. And so we were extremely surprised at the early reports of small ferroelectricity in bismuth ferrite. It should really have very strong ferroelectric dipole interactions, and also very strong magnetism from the iron-oxygen-ion interactions. Okay, so this is our trial compound, and now we go off and calculate the properties. And our tool, our equipment that we use, is a method called density functional theory, which is perhaps the workhorse of electronic structure computational materials. It was developed by my colleague, former colleague at Santa Barbara, Walter Cohn, who received the Nobel Prize for its development. And what it allows us to do is to solve the Schrödinger equation for an interacting many electron system, which in general we can't solve directly, by mapping it into a system of non-interacting electrons in which one electron feels just the mean field, the average of all of the other electrons. And it does this via a system of equations called the Cohn-Sham equations. Now remember, I said to you earlier, the reason that we were interested in transition metal oxides is because of these so-called strong correlations in which the electrons really are not mean field-like. So there's an obvious problem with making this mapping, and we have to be very careful in the way that we then incorporate beyond mean field correlations. And there are very well-established ways for doing this in this so-called exchange correlation term for materials that are not multiferroics, but we have to be extremely careful when we apply density functional theory to magnetic insulators and to multiferroics to treat this problem appropriately. In principle, though, given that we do that correctly or appropriately, we can calculate all of the ground state properties of the system. So, for example, we calculate the structure, the magnetic ordering, dielectric and piezoelectric response, and with various tricks that we've developed for applying finite electric fields or magnetic fields within the density functional formalism, we can also calculate magnetoelectric coupling. Okay, so bismuth ferrite. After a lot of head scratching and some difficult calculations and really difficult experiments, we converged together with our experimental colleagues into agreeing that bismuth ferrite in fact has a very large electrical polarization, 90 microcoulombs per square centimeter. This is the measured polarization as a function of electric field, and you can see it has beautiful ferroelectric hysteresis. The number here is 60 because this is a 001 oriented film and the polarization is along the diagonal, so this is just 90 cosine theta. And the origin of the polarization really is the bismuth lone pairs. Here are my little these yellow dots are the blobs of electron density above the bismuth atoms, and you can see they line up beautifully. This is calculated electron density through the crystal, and this gives me the very large electric dipole moment. So it's a beautiful ferroelectric material. In fact, probably the one of the most important results out of the multiferroics community has been the identification of this ferroelectric with such a large polarization. It's very magnetic, but unfortunately it's antiferromagnetic. So each individual ion has a very large magnetic moment, but they anti-align. And this was, in fact, in retrospect, obvious. For those of you who are familiar with magnetism, is a very strong what's called super exchange mediated by the oxygen between the ions. So we're kind of halfway there. We have and it does all this at room temperature. We have a very robust room temperature antiferromagnetic ferroelectric. It's still an open problem to find a room temperature ferromagnetic ferroelectric. So you kind of young people about to launch on your careers, I've run out of ideas. I've tried everything I can think of, but I think this is still a challenge. There's no fundamental reason why it shouldn't be the case. It's just we've not got lucky enough yet with our guesses, I'd say. Given that we have at least some kind of magnetic ordering combined with ferroelectricity, I want to show you then how we've been able to go about controlling with an electric field the antiferromagnetism. Now, obviously, we would rather be controlling with an electric field ferromagnetism, but we're at least one step on the way. And the physics that we decided to use is, again, kind of the simplest possible physics. This is also going to become relevant for the electric dipole moment project, which is to recognize that when I make a phase transition from a high-temperature paraelectric phase to a ferroelectric phase, and I develop my spontaneous electric polarization, there's a structural distortion associated with that. And in this cartoon, I've shown it as just a tetragonal elongation. The structural distortion through the magnetocrystalline anisotropy determines the orientation of the magnetism. And so in my cartoon here, let's say the antiferromagnetic moments are pointed perpendicular to the polarization. Now you can see immediately, if I take an electric field and switch the ferroelectric polarization by 180 degrees, I'm still elongated top-bottom and nothing happens to my antiferromagnetic easy plane. But if I reorient my electric polarization by 90 degrees, now I elongate left-right and my antiferromagnetic easy plane has reoriented. So this is the physics that we're going to use to reorient, not to reverse, but to reorient the antiferromagnetic vector with an electric field. In bismuth ferrite, it's a little bit more complicated. Obviously, it's not just a rectangle. It has a real crystal structure. The polarization is along 111. 180-degree reorientation doesn't affect the easy plane of magnetization, whereas 71-degree or 109-degree, the other options of changing the polarization along a cube diagonal do. And we made some rather detailed calculations to figure out where the in these easy plane, the moments should lie in a strained film, and predicted that for 71 degree switching and for 180 degree switching, there's no change in the antiferromagnetism, whereas in 109 degree switching, it should change. I'm going to, in the interests of time, skip over the experimental confirmation of this, but apart from telling you that our colleagues did a combination of photoemission electron microscopy and piezo force microscopy, and really did find that only 109 degree switching changes the antiferromagnetism. So we really do have deterministic electric field control of the magnetism in bismuth ferrite. And again, to do this in a ferromagnetic ferroelectric is of course the ultimate goal, and if someone can please make one, then I think it will be possible. I'm showing you this propaganda. Science magazine lists always its breakthroughs of the year for each year, and at the end of 2007, this development was listed as one, which I thought was very amusing because one of the other developments, I think they choose 10, was the startup of the Large Hadron Collider. And the next project I'm going to show you is actually testing on a tabletop the same physics that will be tested in the Large Hadron Collider. So we're kind of in a hurry to get this next project going before they get the LHC actually running. I think the multiferroics are a little bit ahead still. I talked to some, I'm skip over this one too because I want to really tell you about the theory of everything. But I talked to some of you today about the rich physics of bismuth ferrite that's still taking up a lot of our brain cells. Okay. So again, making a room temperature multiferroic is really, really hard. And so we decided to, it might be easier instead to figure out the origin of the universe or something. And the way that we're doing this is by a solid state search for the electric dipole moment of the electron, not the magnetic moment of the electron, the electric dipole moment. So we just looked in a conventional multiferroic at what happens to the magnetism when we switch by 180 degrees the polarization. And I kind of showed you with cartoons, you can also derive this through Landau symmetry analysis, that if I have the magnetism and the polarization parallel to each other, that's energetically equivalent to having them anti-parallel. When I switch the polarization with an electric field, my magnetism is unchanged. An electron, if it has an electric dipole moment, then the only symmetry, the only quantum number associated with an electron is the spin quantum number. And so the spin quantum number determines the symmetry of all of the observables associated with the electron. And so it sets the orientation both of the magnetic moment, which we're kind of familiar with. In fact, we even use the term spin and magnetic moment interchangeably often for an electron. But the spin determines the orientation of the magnetic moment. It also must, by symmetry, determine the orientation of the electric dipole moment. So a consequence of this is that here's my electron and here's its kind of, this is representing its spin, which determines its magnetic moment and its electric dipole moment. If I either switch the magnetic moment with a magnetic field, or the electric dipole moment with an electric field, the other property is obliged to switch. They're locked together in an electron because there's only one property that's determining both. There's only one fundamental quantum number that's determining both properties. So an electron, in fact, is the ideal magnetoelectric. The spin couples the magnetic moment and the electric dipole moment completely, rigorous, like 100% pinned to each other. Questions? Objections? Okay, silence. It's a little bit worrying. Everyone's gone very quiet. Okay, so this property, the fact that when I switch, actually we're going to use the lower property, the fact that when I switch the electric dipole moment of the electron with an electric field, I also switch its magnetic moment, is what we're going to use to try to measure the electric dipole moment. Or actually, I should use the term, we're going to try to search for the electric dipole moment of the electron. Okay, so here's the experiment, or here's a cartoon of the experiment. I apply an electric field to an ensemble of electrons, and it becomes lower in energy by an amount the size of the dipole moment times the strength of the electric field, for the electrons to have their dipole moments parallel to the electric field than to have them anti-parallel. Okay? So this is like a Zeeman splitting, but for the electric dipole moment, or a Stark effect, I guess. It's a Stark effect. So because now it's lower energy to be parallel than anti-parallel, I have a larger, just by thermal distribution, I have a larger population of parallel electrons than anti-parallel electrons, parallel dipole, electric dipole moments. But because the electric dipole moment has parallel to the spin, I have a larger population of magnetic moments than anti-parallel magnetic moments. Okay. So now when I reverse my electric field, it now becomes lower energy for the electric dipole moment population switches, and so does the magnetic dipole moment population. So there's a change in magnetization between this arrangement and this arrangement, which I can detect with a squid magnetometer. And this is what I'm going to measure, or what my colleagues are going to measure. Why, you may be asking. And the reason is that the electron with an electric dipole moment violates time reversal symmetry. And so so I'm going to illustrate that here. Here's my electron with its electric dipole moment and its magnetic moment. When I apply the operation of time reversal to this electron, nothing happens to the electric dipole moment. An electric dipole is invariant under time reversal. But the magnetic moment, because it's a current, reverses. And so you can see that the electron I end up with after my hypothetical time reversal operation is not the same as the electron that I started with. So an electron with a non-zero electric dipole moment violates time reversal symmetry, and there's a fundamental theorem that states that the product of time reversal symmetry, charge conjugation, and parity is always totally symmetric. So an electron that violates time reversal symmetry violates CP symmetry. Okay? So now it gets really interesting. Various fundamental theories, in particular various extensions to supersymmetry, incorporate CP violation in different ways, and so they predict different distinct values for the electron-electric dipole moment. And here's a plot of their predictions. So this is, first of all, this is the predicted electron-electric dipole moment in electron centimeters. This is really small. To a material scientist, this is basically zero. It's extremely small. The current limit, which is obtained optically, is at around 10 to the minus 26. The projected value from our colleagues at Yale is about 10 to the minus 29 that they think they'll be able to get to if we make them their dream material. And what's exciting is that many plausible theories of high-energy physics predict different distinct values of the electron-electric dipole moment that are above the value that we should be able to search for. And so the plan of the Yale group is they measure and measure and measure, and they get so many statistics, they say, aha, I've reached this value in my resolution. If I haven't found the electric dipole moment of the electron yet, all of these theories are wrong. Or at least they have to go and fudge their parameters to move their predictions down a bit. And of course, if they do measure, if they find a value at exactly here, then split supersymmetry is is consistent with experimental observation. Questions? Have I lost anyone completely? Do you think I'm completely mad? Or this is a nice thing about moving to the ETH is that I don't have to write proposals for everything I want to do anymore, so I can do more and more projects that are completely mad, that no funding agency in their right mind would ever support. So we have many more of such things going on now. Obviously, this experiment is not easy. This is a very hard experiment. So look at what we need here. We need to get a population difference, which is basically going to be a Boltzmann population, between two energy levels whose splitting is given by the product of the dipole moment times the electric field. We just saw the dipole moment is minuscule, really, really tiny. So this splitting is really tiny. We'd like it to be as large as possible. And we need to work at very low temperature to maximize this population difference. To increase the splitting, it's proportional to the dipole moment times the electric field. I can't increase the electron's electric dipole moment, that's whatever it is, but I can increase my effective electric field by using a ferroelectric material, because then the electric field that's felt by the electrons in the material is enhanced by the ferroelectric polarization. So on the shopping list that Steve Lemera's group gave to me of what they wanted, their first requirement was it should be ferroelectric. They need to be able to switch it at liquid helium temperature. They want to work at low temperature, and it should have a large polarization. And this polarization environment must change at the when you switch. They need it to be magnetic, because otherwise all the electrons are going to be paired up with by the Pauli principle. But it must not have ordered at liquid helium temperature, because if it's ordered, then the electrons are locked in to their ordered arrangement and they can't respond to the electric field. They need a bulk sample. They need lots of stuff to get enough statistics, so we're not allowed to play tricks like layer by layer thin film growth to make our material. It doesn't have to be a single crystal, but it could be a ceramic.
Now I do have a question.
Okay.
I don't quite understand. I mean, in principle, what you want to measure is the property of an electron.
Uh-huh.
So what you need is a material that is not, how do you say, that doesn't combine what you talked about before, like that is not, doesn't show an electrical switchable magnetism by material properties. You just want to switch the electrons.
Exactly.
So you must have non-magnetic ferroelectric material.
It-
Now you say it must be magnetic.
It must be. So that's a really good point.
It shouldn't be multiferroic, right?
So yeah, that's a really good point. Could you all hear the question in the back about what about all the issues we've been talking about before? So yeah, so it's actually not multiferroic. That's a very important point. It has to, it has to be not ordered at a few Kelvin for two reasons. One, because if the atoms need to be able to still respond, the electrons need to be able to respond. But also, if it were magnetically ordered, then one would have the conventional magnetoelectric responses that I just talked about. So it has to be, so it's it's not really multiferroic. It has to not be multiferroic. It has to be a very good ferroelectric. It has to be magnetic, but not magnetically ordered. If
It needs to be magnetic. I mean, the electron is magnetic. So
because if it were not magnetic, we'd have equal numbers of up magnetic moment and down magnetic moment electrons. So we'd also have equal. And they're kind of locked together by the Pauli principle, right? By the antisymmetry of the wave function. So I need to have basically unpaired electrons. I need a paramagnet, yeah. So I need to have magnetic ions. I need to have triplet spin states in there on local atoms. So I need to have not had my electrons all anti-parallel in molecular orbitals. I need to have free electrons that are not pinned to the anti-parallel to their neighbors. Because otherwise the molecular, the pairing energy of two electrons in a molecular orbital is going to be far bigger than the switching energy I can provide with my electric field. So it must be locally magnetic. There must be unpaired electrons in the system.
basically free electrons, but of course that doesn't exist. So maybe electrons in a deeply buried shell.
Well, if they were free electrons, they would be, they'd pair up, right? Because that's the lowest energy state. So it has to be isolated, non-interacting, unpaired electrons. Yeah. Or minimally interacting. They must not have, so they have to be disordered, so they have to be paramagnetic, and they also have not to have frozen. So even a spin glass is unacceptable. So this, initially I'm like, haha, yeah, no problem. We've failed for the last 10 years to get a room temperature multiferroic. Now you want me to get one that doesn't order. I can totally do that. But for these issues, it's really hard to get something at 4 Kelvin where the magnetism hasn't frozen in somehow, that it's still basically non-interacting, local magnetic moments. Other questions? Other objections? Go on.
And what about molecular magnets? They were kind of cool then.
Yeah, we don't know if you can get them dense enough. So the other thing I guess in this, implicit in here is I need lots and lots and lots of stuff to get enough statistics. But yeah, I'm not sure if people have thought too much about molecular magnets. Possibility. Yeah, interesting idea. Okay, so let me in the last 5 minutes. Can I go 5 minutes over since we had kind of 5 minutes of questions already? Is that okay? And we still wait. I need to leave time for the student question. So here's what we did. So remember our second approach was to make this ion ferroelectric and this one magnetic. And so here there's many options. All the conventional ferroelectrics have a non-magnetic ion here, for example, barium titanite, titanium 4+. And on the A site, we decided to put a rare earth, a lanthanide with 4f electrons, because the 4f electrons are very, very localized. And so they're our best option for not getting magnetic ordering by liquid helium temperature. Okay, so here was our idea, was to make an alloy of barium titanate, which is not magnetic, it's kind of the prototypical ferroelectric, good electric polarization, with europium titanate, which exists in the same crystal structure. It's magnetic, it's antiferromagnetic, but with a rather low ordering temperature already. It's not ferroelectric, but our idea for why it wasn't ferroelectric is that it has a rather small lattice constant. So there's just not enough room for the titanium to move off center and give electric polarization, in contrast to barium titanate, which has a rather large lattice constant. And so our kind of guess for the phase diagram, so our cartoon guess, was that, well, if we make an alloy, we'll dilute the europium and start suppressing the Néel temperature, and we'll increase the lattice constant and hopefully grow in a ferroelectric polarization, and maybe there'll be a regime where we get a large enough polarization and we've suppressed the ordering enough that it has the properties that we want. So then we went away and made calculations using density functional theory. I could not persuade any of my students or postdocs to make these calculations. I would walk around the office jumping up and down excitedly, and they'd all kind of avoid eye contact. But fortunately, Mariana Lejajic, who was visiting me at the time, persuaded her postdoc, Kostya Ruchansky, to make the calculations. And the calculations were actually not very demanding. They used very standard methods, standard techniques. We made ordered supercells because in our calculation we have periodic boundary conditions of europium and barium. And we started with the 50-50 alloy because that was just the easiest for us to calculate. We found that it has a rather nice electric polarization and very large displacements of the europium, which switch when the polarization switches, and the magnetic interactions are very strongly suppressed. So exactly as we expected. In fact, I was giving a similar talk to this at the physics colloquium in ETH a few weeks ago, and somebody afterwards said to me, I really don't know why you bother with the density functional calculation. It was kind of obvious it would do this, which I thought was a bit rude, actually, for him to say that. But it's very true. Probably shouldn't have pointed it out. But okay, so we have what we exactly in our density functional calculation. Actually, this plot doesn't fit. What we calculate is what we want. So now we had polycrystalline ceramics synthesized by Stanislav Kamba in Prague. And here's the dielectric constant as a function of temperature. This divergence at 200 Kelvin is the onset of the ferroelectric phase transition. Here's the ferroelectric hysteresis loops. The magnetic susceptibility is a function of temperature. Doesn't start to diverge, indicating magnetic ordering, until well below 2 Kelvin, and so we have beautiful paramagnetism at 2 Kelvin. So we really have our complete rational design of a functional material with exactly the properties that we want, or exactly the properties they told us that we wanted, which turned out to be not quite right. So now the material is in this cryostat at Yale, which actually is not quite tabletop. It goes down into the floor here, and there's a big magnetometer down here, and they're measuring and measuring, and this is Stephen Eckel, who's the graduate student who's sitting down here measuring and measuring. And this plot is unchanged from 6 months ago when they gave me where they were at, which is actually not bad already. They now have sufficient statistics to say that from their experiment, the electron electric dipole moment must be larger than 10 to the minus 23, which is the same resolution as the previous best solid state experiment. They've not yet been able to reach where they'd hoped to reach within 6 months of averaging. And the problem that they're having is that when they make the switching, they have thermal hysteresis. So they're having problems with the calorimetry, with controlling the temperature. So our plan, our kind of next step with this is, in collaboration with Anke, to grow single crystals of europium barium titanate. And we hope that without the grain boundaries and the polycrystallinity, we'll be able to have a better control of the thermal properties. Otherwise, we have to come up with a new plan. Okay, so hopefully I've given you a little bit of an overview of some of the areas of multiferroics and magnetoelectrics that are interesting for device applications, for their fundamental physics, and also some kind of wacko applications, and convince you maybe that density functional calculations are useful in designing them. And let me put up my absolute favorite propaganda that came out of this last study while I take any other questions you have, and particularly the student question that I'm eagerly awaiting. That's it. That's the end.